Right. Yep, so got a lab today. Yep. All right. So this is where we left off. Yep, I got it. Yep. All right. So we have standard deviates. So we learned discrete distributions last week. We're starting with continuous distributions, and the one we're focused on is the normal curve, because this kind of gives you the introduction on how to calculate probabilities. Why do we worry about it? Because probabilities, these probabilities, are the p-values. Right? So when we calculate p-values and assess significance, this is what we're doing. All right. So in order to calculate a probability from the normal curve, if we did it by hand, what we will do is calculate a standard deviate, which is also a z-score. You'll see this is reported as a z-score test, possibly. But what we're doing is converting all of our x values so that our new x values have a mean of 0, standard deviation of 1. And once we have that, then we can use our regular standard tables. R does this. All right? We don't have to do it in R. We just tell R what our actual distribution is, what our mean and standard deviation, and then R will calculate the z-score for us, and then return the probability. All right? So our choices So we talked about applications. So what we're doing, and what we're going to do is learn this basic one. So what's the probability of finding an individual smaller than a value, or between values, or greater than some values? And that is directly related to a p-value, which is the probability of getting data as extreme or more extreme than chance alone, if our null hypothesis is true. So we kind of set it up and say, this is what we observed. How likely is it the chance would give us, the chance could produce a more extreme value? That's an area under the curve. All right, so our options are to use these normal tables. All right, so we've got two normal tables to choose from. We've got, and I have them both posted. Let me open up one. This is it. There it is. All right, so here is one. This is my normal table.pdf. All right, so this table gives the area to the left of our point. And it only gives us the positives. All right, so it's only listed in the positive. Move that down. So our first one is probability that our value, or probability of finding a value that is less than or equal to some given value. So we could say, you know, our population is, let's say, mean of 15, standard deviation of 3. All right, and we find an individual that measures 11 units. We could ask the probability, ask for the probability of finding an individual that is 11 or less from this population. And that is kind of what we can use. That's to the left. The second page gives us to the right of that value. And you'll note that this is greater than or equal to, and the other one is less than or equal to. And that is standard for continuous distribution, because the difference between, you know, 0.0000000, you know, to like the 20th zeros and 20th zeros and a 1 at the end is basically negligible. All right, so no matter what, we don't have to really worry about, the greater than or equal to sign. This one gives us less than or equal to z. That's standard, so it includes that value. This one does not include that value, but in reality, there's really no difference. Right? It's minuscule. All right, so this is the table that I prefer. We can also use the other one that is posted. Gives us a one-sided. I am going to show you how to use this table. So let's just give an example. All right, we're going to work with the normal 0, 1. So I'll change that and I'll just say z. All right. So we want to ask, what's the probability that we find a z that is less than or equal to 0.77? All right, that's our question. Make sure up here. Move this. There we go. That's better. All right, so that's what we're looking for. Those of you at home. Z is less than or equal to 0.77. All right, so how do we look at this table? So at this table, we're on this side. So if we drew a curve and said, what area are we looking for? Well, our histogram is centered at 0. All right, standard deviation of 1, that's given to us. And we're asking 0.77. That's our value. All right. This question is asking for that total area. Area to the left of 0.77. So in our handout, that's what this area is. The question is, what is 0.77? So we read down the column to 0.7. All right, there's our 0.7 right here. And then we read across the row until we get to the 0.07. So this value here, 0.7794, is the probability that we get a value less than or equal to 0.77. All right? Not too bad, right? So read the column, that's our tenths, and then hundredths is across the row. Our hundredths is across the row. What if we changed it? What if we, and I should, before we move on, does that make sense? It should, all right? It makes sense because we're over 0.5. So the area to the left of 0 represents 50% probability, right? So we know we're at least 0.5, and then we're just going to go up to 0.77. Now we can, if you remember those approximations, like 1 standard deviation, 2 standard deviation away, I look at percentages, that could help you with stuff. But for this, I think it just makes sense to know that we have a value of 0.7794. What if we ask the flip side? What if we ask, well, what's the probability that if we get a value that is greater than or equal to 0.77? So now, there's our 0, our 0.77 is at that point. Now we're asking for this area. So we're asking for the tail, all right? Now, we know the area under the entire curve has to sum to 1, right? Right? All right, so we already know to the left of that line, so we could do 1 minus this value to get our answer. Or we recognize that we're in the tail, and that's what this side, this is what this second page is finding for us. So same thing, we go down to 0.7, we read across to 0.77, and we get our value, 0.2206. It is 0.2206. Right. Does that make sense? Yeah, we don't have half. We didn't cover half of our tail, so half of that tail is 0.5. We're below that, so we should have a value less than 0.5. And does it make sense, 0.22? Well, it does to me because we have already found that one. or to the left of that point. But, we're not a full standard deviation. Right? 2 standard deviation away constitutes about 95% of our values. So that gives us 2.5% in each of our tails. Right? We're not at that. 1 standard deviation is 68%, about 68%. So that means we have, what do we have? 16% in each tail. So we're not quite at a full standard deviation of 0.77. So yeah, 0.22 kind of makes a little bit of sense. All right, so we're going to use this table as practice. So here's our example, and this one's going to be a little bit harder because we're not working with the 0, 1 normal curve. So wing length of roaches follows a normal distribution with a mean of 15, standard deviation of 2. All right, so our question is, what's the probability that we're going to find a roach that has a wing length of less than 18? All right. So that's like the mathematical term in word form. What's the probability we find a roach with wing length smaller than 18 millimeters, or however many lengths we have? All right. So first up, we draw what we're looking at. All right. So this is our curve, normal curve, bell curve. All right. We're centered at 15. That's what we have. There's our center, right at 15. We've got standard deviation of 2. All right. And what we're asking for is this area, the area to the left of 18. That's the area. So I know when I go back to my normal table, I'm using that area. This is the table that we're going to use, that side. All right. Now, that table is normal 0, 1. So what we have to do is convert our value to a z-score. So I start off with the probability that x is less than 18. I start off with that probability. And then I use that equation, that z equation, which was our value x minus the mean divided by the standard deviation. So z is x minus our mean divided by our sigma. Right? That gives us a z-score. So what I'm going to do is, in our inequality, I'm going to do that to get z. But if I'm going to do it to the left-hand side, I have to do it to the right-hand side. Remember that from algebra. So the right-hand side, I have 18 minus 15. That 15 came up here from the problem. We're going to divide it by 2. So that converted it from x is less than 18 to probability that z is less than 1.5. So now, once we have our z, now we go to our table. And we said it was 1.5. So I scroll down to 1.5. It is 1.50, so it's that, 9.332. Now, does that kind of make sense? Well, yeah, it does. We're over 0.5 because we have half of a curve and then some. Right? Does the 93 make sense? Yeah, again, to me it does, because 2 standard deviations either way gives me 95%. We're not quite at 2. We're at 1.5. So we're going to be between that 68% and 95%. But we also include the other tail. We're not talking about between our 2 values. We're not saying between 1.5 and 1.5. We're talking from 1.5 all the way to the left. So yeah, it kind of does, to me, make sense. You'll probably get a feel for it. If anything, I need you to recognize that when you calculate this, and we have a situation like this, our probability should definitely be above 0.5. If it's not, check, make sure you're using the correct table. All right. All right. So here's some practice problems. All right. So here's some practice problems. Population of worms has an average length of 28 millimeters. With sigma is 3.5. What's the probability that you find a worm that's larger than 33 millimeters? All right. We've got an average score, NFL games, average length of mobile phone call, average height of U.S. men. All right. So what I want you to do is take some time, see if you can answer these. Try to answer these questions and come up with the answers. I'm going to give you probably 5 minutes or so to do these. And remember, in order to use the table, we're going to have to convert these values to a z-score. And it will definitely help you to draw that curve on a piece of paper to know what area you're actually looking for. And you'll note you do have to round to the hundredths place on all your calculations so we can use the table. Okay. going? Do you have answers for all four? No? Still working?
I'm gonna wait real and figure it out.
What's that?
I'm a little behind. I'll figure it out. If you're waiting on me to figure it out.
I bet you're not the only one. So let me move the camera. I will keep the camera small so that I don't get people sick. I know we don't do a lot of this stuff by hand, but you have to learn how to do this by hand so that you can do it in the computer. All right, let me enlarge this image. So hopefully everyone has this information down, hopefully. Those of you at home, this will get covered up. All right. Wonder if we got a good piece of chalk. All right, so question one. Population of worms has an average length of 28, a standard deviation of 3.5. What's the probability that you find a worm that's larger than 33 millimeters? So, we are asking that probability that x is greater than 33. All right? I'm going to draw this curve. We are centered at our mean, at mu. So the average length is 28. All right? We're looking at 33. We're looking at that, and we want this area. That's the area that we want. So that is the probability that x is greater than 33. That's our area. All right? And this is comparable to a p-value that you'll see going forward. All right? So how do we do that? Well, we have our x population is a normal curve, mean of 28, standard deviation of 3.5. All right. So what we're going to have to do is go to this, and we're going to subtract our mean and divide by our standard deviation. All right. And when we do that, what we've done is taken x and converted it to a z. And now what we're working with is standard deviations. So it's no longer, let's say this is millimeters. We're no longer asking what's the probability that we'll find a worm that's larger than 33 millimeters. At this point, we are asking what's the probability that we find a worm that's larger than 1.43 standard deviation units away from the mean. All right? That right there allows us then to use our table. So I look at my table, and I realize that I'm actually looking at this tail region. So now I just go down to 1.43. So 1.4, I read across to 0.03, and I get 0.0764. And that's our probability. All right? You get that? All right. Number two, average score of an NFL game. All right, so this is number two. I'm going to draw my curve. All right, so let's say this is our average score of the NFL games. All right, it's 21.7. That's our mean. All right, we're asking what's the probability of having a score that's less than 9. We are at 9 and we want less than, so we are looking at that tail area. So that area right there is the probability that x would be less than 9. Right? In order to use the table, we have to subtract our mean and divide by the standard deviation. So now what we have is a z, that gives us our z, and I have negative 1.25. you get? All right. Now, we don't have negatives on this table. Why not? We need negatives on this table. Exactly. So our left and right hand sides are mirror images of each other. All right, they're mirror images because we're centered at a mean. Right, we're symmetric. It's kind of what symmetry means. And yeah, we're dealing with standard deviation. So one standard deviation below the mean is the same as one standard deviation above the mean. So this 1.25 is the same thing as saying z is greater than 1.2, positive 1.25. It's the tail. That tail is the same as this tail, which is 29, 30, 30.7. What's the difference? 30, 32? 34.4. So however many units that is. This area is the same as that area. So once we know that, then we can easily just look at our table of 1.25, and we're going to use the tail part. I go 1.25, 1.2 down my column. I go 5.05, and I get 1056. 105. And I can tell you why I got that probability, why I picked that one. Because one of the major yeast suppliers has an American ale strain labeled 1056. That's their number. It's called the Chico strain out of Chico, California. That was Sierra Nevada's strain. When I saw 1056 in the table, I said, okay, how do I get 1056? I had to get my number. All right, so far, just remember, we're mirror images. If we have the negative values, all we have to do is flip it to the positives. But if you're going to flip it, remember to flip the sign. So it goes from less than negative 1.25. When you change it, we have to go to the larger to greater than positive 1.25. No, this is a rule of working with inequalities, and you probably covered it in middle school. And then worked with it again in high school. And in college algebra. All right. Question 3 is now getting a little bit harder. And this is, so hopefully you can see why, the benefit of looking at these areas kind of gives us an idea of which side of this table to use. So question 3 now is asking between values. So the average, when I made this presentation, the average length of a mobile phone call was 1.78. 1.78 minutes, believe it or not. I made up that standard deviation. I couldn't find it, so I just said 0.6. That's why I had an asterisk by it. But question 3, we want to know an area between two values. All right? So there is our curve. We're centered at 1.78. And now we are asking for a phone call that's between 1 and 2 minutes. We'll say that's our 2. We'll say this is 1. So what we're looking for is this area here. Okay? How might we approach this problem? Yep. All right, so we're doing this. That's what we're doing. So in order to approach this, the way that I recommend doing it is by figuring out the area, x is less than 2. What we're doing is going, there's our 2. We're doing this entire area first, and then what we'll do is cross out that area. So we're going to find the bigger of the area, and then we can find the smaller of the area. So once we have that, then we can say, well, let's find the area to the left of 2 and subtract out the area to the left of 1. All right? So how we actually write it out is up to you. I actually did everything to the z-score up to this one first, but we'll work these out. So same thing, we just subtract your mean, divide by the standard deviation. And that gives us our z. 0.37. Then this one, negative 1. All right, the same sort of thing. What we can do is convert this to a positive. So that's our tail. So z is less than 0.37 minus z greater than 1.3. I have, I'm going to move up here. 0.6443. We subtract out 0.0968. And that gives me a total probability of 0.5475. All right. Not bad. All right, the last one is work. We work it out the same way. All right. So you know the area that we are looking for. So our area, average height is 70 inches. We are looking for 68 and 65. We are looking for this area here. So we want to know the probability that our x is less than 60, or it's greater than 65, but less than 68. So we can split it up and say we want to figure out the entire area to the left of 68, and then subtract out the area to the left of 65. That's kind of what we're doing. Same idea. We're going to do everything to the left, and then subtract out that part that we don't need. All right. So we're going to do our z-scores. X minus 70 divided by 3. Minus. All right, so we have our z's. Smaller. Oh man, not my day. All right, so this is less than 2/3. So I'm just going to do 0.67. All right, 0.67, and then I'm going to subtract out 1 and 2/3. 1.67. Negative 0.67 and negative 1.67. So we're in the negatives. All right. So we can flip them all to the positives. All right. So probability that z is greater than 0.67 minus the probability that z is greater than 1.67. So that leads us to the second page. And when we use that second page, we get 0.67, go down to 0.6, read across 0.7, and I get 0.2514. And I'm going to subtract out the 1.67. So go down to 1.6, read across 7.0475. And then that gives me a total of 2039. Right. Get that? All right, so it's not terrible. It's not terrible. But we go through this exercise because we need to know those portions. Figure out which ones, just kind of keep track. Now, is this the only way to do it? No, it's really not. I mean, we could do to the right of 1 and subtract out that tail. Right? There's different ways to kind of go about getting this slice. How you do it, as long as we get the same number, that's fine. But here, I got to this point where everything was negative, and then I went ahead and flipped it. Flipped it to the positives and worked with the left-hand side. So calculated to the left of 1.67 and subtracted out to the left 0.67. I arrived at the same answer. All right. Any questions? All right. We'll have some practice for this as well. All right, so how do we do it in R? It's actually pretty easy. All right, so the default for R is to assume a normal 0-1 distribution. And we calculate our probabilities by using P norm. So this is different. All right, so for the discrete distributions, we use D binom, D poise, to calculate a density. That gave us the height of the curve, all right? We don't want the height of the curve because in a continuous distribution, that's not what we're looking for. We need this slice. We need the area under the curve. And for that, we're going to use P norm, all right? So P norm will give us that slice, all right, to the left or to the right of some value. So our value that we're interested in is x. So we want the probability that we get a value less than or greater than, less than, or greater than this x value, all right? And we're working with a distribution with a given mean and a standard deviation. Now, again, if we leave off mean and SD, if we don't give it to R, it assumes a 0-1 distribution. It assumes a 0-1. So we could go through and manually calculate the Z ourselves. I'd say, why do it? Why bother? R has the cheat right here. We just say mean equals whatever the mean is, SD equals whatever the SD equals, and let R handle it. Now, are we to the left or to the right of that point? That's our question, and that's determined by lower dot tail. So are we looking at the area to the left of our line, the lower dot tail, or are we looking at the upper tail? So our lower dot tail is going to be either true or false. And to report true or false, we can write true in all caps, or we can abbreviate. So I abbreviate. So if we want the area to the left, we use lower dot tail equals T. So we are looking for the lower part of the tail, so that the area to the left of our x. If we're looking to the right of it, then we do lower dot tail equals F, because it's false. We don't want the lower tail, we want it the upper. All right, so here's an example. If the wing length of roaches is a normal distribution of 15 and 2, then what's the probability we find a roach with a wing length of 18? So this is the exact same example problem that we worked with up here, right, where I showed you how to do it, how to calculate the Z and how to use the table. Well, in R, all you have to do is say, I want P norm of 18. All right? And the distribution that I'm working with is a mean of 15, standard deviation of 2, and lower dot tail equals T because we want to the left of that point. We didn't do our Z's. R is going to do it. And when we hit enter and run it, we get 0.9331928, which is basically the same thing that we got. I'd say basically, did we round? I can't remember if we had to round at any point. But if we don't have to round, we'll get the exact same number. A few more decimal places. The table rounds to 4 digits. All right. So you might notice the 4th digit is different, but if you rounded what R gives you, you'll get the same values that's in the table. Also consider that, on these, this was, 3 over 2, so 1.5. If we had like what our last example that came up to 0.67, R is going to use 0.66666 repeating, which can give a slightly different number because we rounded before we found the probability. All right, so this is what we want to do. We already worked these by hand. We know what we're supposed to get. So what I want you to do is do this. You can start working on it now, or when we come back for lab, while I'm getting stuff set up here, you can work on it. Doing this in R, we'll check our answers in the hands, and we'll work with it in R. All right, so we'll do this in lab. All right, any questions? Yes?
What happened to the cutoff value if it looks like less than or equal to? That's just the less than.
Oh, that's why I said it doesn't matter with our continuous distributions.
Oh, okay.
Because if you include that one point, you're adding an infinitesimally small value, and it becomes negligible. So like if I ask, what's the probability of getting 18 inches? All right, exactly 18 inches. That probability is actually 0, or pretty darn close to 0, because 18 inches is different from 18.000, 100 zeros with a 1 at the end. All right, we're dealing with an infinite number of possibilities. So that's when we do the less than or equal to, we get the same value. Discrete distributions are different, and we'll see that when we do like a binomial test or a Poisson test, because we can do the same thing, calculate areas to the left of those curves as well. That's where it becomes important, not for the continuous distributions. All right? All right, we'll see you at 2 o'clock.